All right, guys. So in this video, we're going to be going over dimensional analysis. Okay, so I'm going to show you a bunch of examples, how to set up different problems, how to find equalities to use in your dimensional analysis given different measurements. So equalities that you might already know versus equalities that you have to kind of not make up, but have to interpret based on given information. And then, how to do your dimensional analysis setups. And then, at the end, we're going to start sprinkling in the concept of a mole, which is 1 mole of something equals Avogadro's number of those somethings. So normally we're talking about particles. So 1 mole of an element equals 6.02 times 10 to the 23rd atoms of that element, particles, atoms of that element. If you talk about a compound like water, 1 mole of water equals 6.02 times 10 to the 23rd molecules of water. The word particle, the word we use for a particle of a compound is molecule, and the word that we use for particle of an element is atom. So, but really, all the concept of a mole is, and we discussed this in class, is just like a dozen. So, a dozen something equals 12 of those things. A mole of something equals 6.02 times 10 to the 23rd of those things. And in chemistry, those things are atoms and molecules generally. Okay, there'll be other words for different types of particles that we'll find, we'll get the vocab for that later on. Right now, just think atoms, molecules, and if you just want to use the word particle, you can just use the word particle. Okay, the other concept that we're going to start getting into is molar mass, okay, and how you can find the molar mass. Now, I'm just going to show you how to use, if you know what the molar mass of something is, how to use it in dimensional analysis. There's notes that you should look over, and we'll be talking more in depth on what molar mass is. So I suggest you read over the notes that you get in class on molar mass, how to use it. But today's lesson, again, is just going to focus mainly on dimensional analysis. So if you know what molar mass is, or you're given the molar mass, how do you use it in dimensional analysis? Okay, so that's essentially what we're going to be talking about today. So before you kind of watch the rest of this video, you should go over the notes that I'm going to highlight here. Okay, so first the dimensional analysis notes. Okay, I have a video going over this a little bit already, but you want to maybe just read over this because I'm going to use terms like conversion factors and all this stuff that we've talked about in class, but you really need to get a firm understanding of what all this stuff is. So this shows you different dimensional analysis setups with the metric system, your metric equalities. So the other thing you might want to look at are the metric equalities that you're responsible for. So this handout that you got, and also not molar mass notes, but what am I looking at? I think it's this. So, knowing that a centimeter is the same thing as a millimeter, like milliliter, knowing that equality might help you out with dimensional analysis, and knowing this stuff too. So you might want to read that handout. Okay. The other thing is using molar mass. This shows you how to use how to use molar mass in dimensional analysis. And then just what molar mass is, how you find it, using your periodic table to get there. Now, again, this is all stuff we're going to cover in class, and I'm going to show you. But, you have notes that you can read about it. You have these videos you can watch. So, it's not just in class where you can find all this information. Okay? All right, so let's get down to it. If you look at your dimensional analysis notes, the main thing I want us to understand is dimensional analysis. We're taking a measurement that we have. So in this case, it was 1,590 grams, and we're multiplying it by a conversion factor. And a conversion factor is this ratio. And we get this ratio based on an equality. So I know that 1,000 grams equals 1 kilogram, right? So that's a metric equality that you should memorize, that you should know. Okay, and it doesn't have to be just grams. Just 1,000 base units equals 1 kilo of those units. Okay, so you know, you could change this with meters. So 1,000 meter equals 1 kilometer, or you could replace it with liter. 1,000 liters equals 1 kiloliter. The important thing is that you know that equality. And now, if you have an equality, you can make two conversion factors. I can say this part of the equality divided by this part of the equality, or I could switch it and I could say this over that. And the one that you're going to pick is you're going to cancel out the units you want to cancel out and get the units that you're trying to get to. So in this question, we have grams and we want to cancel out grams and get to kilograms. So if I have grams on top, how do I cancel out grams? I need to get grams on the bottom. So that's why I take this part of the equality and I put it at the bottom of the ratio. I take this part of the equality and I put it at the top of the ratio. And now mathematically, all I have to do is take my measurement, multiply it by this number that's on top, but it's just 1, so I don't really need to do that in my calculator. But I would take this number, multiply what's on the top, divide by what's on the bottom. Grams would cancel out because I have grams on the top over here. In the numerator, I have grams in the denominator. Grams cancel out, and the unit I'm left with is kilograms on the top. So if I just take this, divide by 1,000, I get my kilograms. Okay. Now again, a lot of you will say, I already know how to do that. I don't need to do this dimensional analysis setup to do this conversion. I already knew how to do it without showing my work. And what I'm telling you is you need to get good at using dimensional analysis, practicing with the metric system, because you have other ways you can check yourself, and just get good at setting up dimensional analysis, things like this. And they don't have to look like this. I'm going to show you different ways. And they can be, you can have multiple conversion factors. You could take a measurement and multiply it by a bunch of different conversion factors to get the final answer you want to. It might not just be in one step. So that's one way, one thing. And the other thing is understanding when you're given units like this, and I'll have plenty of examples coming up here in a second, but grams per milliliter. So we know that's a density, but it doesn't matter if it's a density or a speed or something else. If it's this unit divided by that unit, so grams divided by milliliters, okay? We should interpret this as an equality. So this, in the notes case, this was the density of copper, okay? So the way to interpret this is 8.96 of these units equals 1 of these units. So 8.96 grams of copper equals 1 milliliter of copper. And notice that I said 1.00 milliliters of copper because I'm maintaining the significant figures. So the density 8.96 has 3 sig digs. So the equality I can make with that measurement, it's 3 sig digs for each of those measurements. Okay, so if this had been 8.960 here, then I could have put 8.960 here in my equality, and then I could have added a 0 here to maintain my number of sig digs. Okay, but you don't have to do that. It's just saying. So if you just wanted to say 1 here, that's fine. Just understanding that if I'm going to use this measurement and I'm going to make it into a ratio to convert from one thing to another, okay, this ratio has 3 sig figs, so I might end up being limited to 3 sig figs. All right. So let's do some dimensional analysis practice. Okay. Whoops. Let me find it. Here we go. All right. So how many seconds are in a year? Okay. So equalities that you should probably know by this point in your education. So I know 365 days is 1 year, 24 hours in 1 day, or 24 hours equals 1 day, 60 minutes equals 1 hour, 60 seconds equals 1 minute. Okay. So 1 year is what I have, but I want to know seconds. So the way dimensional analysis always works is take the thing that you have, 1 year, put it at the start, and then start using ratios that come from equalities, okay, to cancel out the units that you want to cancel out and get to the units that you want. So from this equality, I would put 1 year on the bottom and 365 days on the top. The reason I'm going to put 1 year on the bottom is because I want years to cancel out. Okay. And then so if I do 1 times 365, years will cancel out and then give me days. Okay. Well, I want seconds. So we keep going. So I'm going to use this equality. Well, I'm going to put days on the bottom because now I want days to cancel out and they need to be on opposite sides, and 24 hours on top. Okay. All right. Then I'm going to use this equality, and I'm going to put 1 hour on the bottom because I want hours to cancel out and I want to be left with minutes. So I'll put 60 minutes on the top, 1 hour on the bottom. Okay. And then finally, I'll use this equality. I'll put 1 minute on the bottom. So minutes cancel out, put 60 seconds on top. So I'm left with seconds. So notice seconds doesn't cancel out. That's the unit I'm left with. And now mathematically, I just multiply by all the numbers on the top. I divide by all the numbers on the bottom. In this case, they're all 1. That's not always the case. Sometimes it might be 2 different numbers and you have to multiply by this number and then divide by this number. But since this is 1, I don't have to worry about that. So it would just be 1 times 365 times 24 times 60 times 60. And I get my seconds. Okay. Now, another thing to understand about dimensional analysis is this ratio is equal to 1. How do I know this ratio is equal to 1? Because it comes from an equality. If these two things are equal, then this over that equals 1. And I can flip it. This over that equals 1. So all I'm doing is taking my initial measurement, which is 1 year in this case, and I'm multiplying it by 1, and I'm multiplying it by 1, and I'm multiplying it by 1, and I'm multiplying by 1. And so the value hasn't changed. And so what we should understand is after we do the dimensional analysis, whatever we started with, 1 year in this case, equals whatever we finish with, that many seconds. This amount of time is the same as that amount of time. So, if it takes 1 year for you to do something, and then somebody else says, no, it takes, 31,556,926 seconds to do something, it's the same amount of time. It's just, how you report it. Okay. So let's do this question. You travel at an average speed of 45 miles per hour. So miles per hour. Okay. So the first thing you should think is that means 45 miles equals 1 hour. That's how you should interpret that measurement. 45 miles equals 1 hour, especially if our goal is to really learn about dimensional analysis. Okay. And we want to know the average speed in miles per minute. Okay. So we have miles for every 1 hour. We want to know miles per every minute. Okay. So it's just unit conversion. So I want to take the same speed, 45 miles per hour, and I want to know how many, that's what that speed is in miles per minute. So I'm not going to change the value of the measurement, just the unit. Okay. So we're converting this to this unit. So our goal is we want to cancel out hours and get minutes. But notice where hours and minutes are in the units we want. They're on the denominator. Okay. All right. So we know the equality for minutes to hours. 60 minutes equals 1 hour. Okay, great. So the way the setup should be is I'll take the measurement that I was given. Now, 45 miles per 1 hour. That's how this measurement would look in a dimensional analysis setup. Okay. And then I'm going to take this equality and I need to set it up into a ratio that's going to cancel out the unit I want. Now notice I want to cancel out hour. And so I'm going to put hour on top in this case because I have hours on the bottom here. And so in order to cancel out hours, I need to put hours on top in my ratio there. So I'll put hours on top and 60 minutes on the bottom. So notice hours cancel out here. Okay. And what are you left with? You're left with miles on top and minutes on the bottom. That's miles per minute. So you end up with the unit you want. And now you just have to do the math. So 45 divided by 1. Okay, so 45. And then 45 times 1. And then divided by 60. So 45 divided by 60. So 0.75 miles in a minute. Okay, so all we did there was take 45 miles per hour and figure out that that's equal to 0.75 miles per minute. Okay. And this would be our dimensional analysis setup. That's all. Okay. Now, again, you don't need the multiplication sign there. You could set it up like that with parentheses. You could set it up in a T-chart like I've shown you in class. That's not a big deal. Okay. I just want you to see how the units are canceling out. They only cancel out if they're on opposite sides of the numerator denominator line. I always, in class I say they only cancel out if they're on opposite sides of the train tracks, right? So, like if I had put hours on the bottom here and minutes on the top, nothing would cancel out, and I'd end up with some weird unit, miles times minutes over hours squared, right? So just, that's why it's important to, write down the units. Now you can abbreviate the units, but you want to see them cancel out properly, and you want to see that we're left with the units that we want. So miles on top, minutes on the bottom in this case, okay? All right, so we're given the density of water is 1 gram per milliliter. So remember, that's going to be an equality. So that measurement we can turn into equality. How many pounds of water are in 12,000 liters? Okay, so we're given a volume of water, we're given water's density, and we want to figure out the mass, but in pounds. Okay, so there's a lot going on here, right? We want the mass in pounds, but the density is measured in grams. The density unit of volume is milliliters, but the initial measurement of volume that we have, 12,000 liters, is in liters. Okay. Now, one thing I would give you for this problem is this equality. This is one that you wouldn't have to memorize, but this would be given to you. Okay. But the other things that you would have to know to solve for this question are this equality, 1,000 milliliters equals 1 liter. Okay, I'm going to show you how it's going to work in the setup, but you would have to know that. And 1,000 grams equals 1 kilogram. So again, memorizing your metric equalities. Now the other, why did that happen? 1.0. Okay, I don't know. I'm just going to center this. No. Okay. All right. The other equality to come up with that you're given, but you have to figure out that you were given it, is the density. The way to interpret the density, 1 gram per milliliter for water, is 1 gram of water, and it should be 1.00 for sig dig reasons, 1.00 grams of water equals 1 milliliter of water, right? So that's an equality that we get from that unit, grams per milliliter. So I'm going to need this equality, I'm going to need this equality, I'm going to need that equality, and I'm going to need the density equality that I'm given. All right. So when we start our dimensional analysis, again, our whole goal is figure out how many pounds this much water weighs. Okay. So 12,000 liters, right? So the first thing I'm going to do is get liters and convert it to milliliters. And the reason I'm going to do that is because the density was mass per milliliter, not mass per liter. So I'll take this equality and I'm going to put 1,000 milliliters on top, because that's the unit I want, and I'm going to put 1 liter on the bottom, so that's going to cancel out liters. So if I do 12,000 liters times 1,000 milliliters over 1 liter, so if I do 12,000 times 1,000, that'll cancel out liters and give me milliliters. Now that I have milliliters, I'm going to use the density to convert milliliters to grams. So I'm going to take my 1 gram of water, I'm going to put that on top here. I'm going to take my 1 milliliter of water, put that on the bottom. Now that's going to cancel out milliliters and get me grams. Okay. And then I don't have an equality for grams to pounds, but I do have kilograms to pounds. So I know how to go from grams to kilograms. So that's what I'm going to do next. Once I have grams, I'm going to put 1,000 grams from that equality on the bottom. I'm going to put 1 kilogram on the top. That'll cancel out grams and give me kilograms. And now to cancel out kilograms and get to pounds, I'll put 1 kilogram on the bottom from that equality that was given to me. I'll put 2.2 pounds on the top. And now I just have to do the math. So again, it's multiply by all the numbers on the top, divide by all the numbers on the bottom. So notice the numbers on the bottom, there's only one that's not 1, and it's here. So I'm going to end up dividing by 1,000. So it would be 12,000 times 1,000. This is times 1 divided by 1, so I can kind of skip that in my calculator. So 12,000 times 1,000 divided by 1,000 times 2.2. And that gives me how many pounds that much water would weigh. Okay? And that would be my dimensional analysis setup. showing the units canceling out, and I'm left with pounds. What if they wanted to know how many tons that is? Well, hopefully we know, this equality, 2,000 pounds equals 1 ton. So now I'll just take my pounds and I'll come up with a ratio that's going to cancel out pounds. How do I do that? Okay, well, that's the equality. I'll put pounds on the bottom to get them on opposite sides of the train tracks. And so that'll cancel out, right? That'll cancel out. And so if I just take my pounds, divide it by 1,000, multiply it by 1, and I get my tons. Okay? All right. So let's do another one. All right. So what you're going to notice is as you get better with dimensional analysis, like if you really get good with dimensional analysis, you'll be able to answer some advanced chemistry questions without even knowing what the units mean. You just know that, okay, I got to cancel out this unit to get to that unit, and this is what I would do. And even though I might not know what these units mean and what I'm really calculating, I can figure out a correct answer on a test or something. Okay, so, we will learn all of this stuff, hopefully, but when in doubt, let the units help you out. Let the units do the work if you understand dimensional analysis. Okay, so let's see, we're given this question. The molar heat of fusion for water is 6.01 kilojoules per mole. Okay, you might not know what that means. Molar heat of fusion, all right? And it's this measurement. Now, the only thing I want you to understand now, well, hopefully, kilojoule or joule is our SI unit for energy. So, this is energy per mole is what we're saying. And mole is amount of substance, right? So, but even if you didn't know what that meant, we have units like this. So remember, you could say 6.01 kilojoules equals 1 mole. Okay, and the substance in question here is water. Okay, and the question asks how much energy would be required to melt 25 moles of water, and it's a multiple choice question. So the first thing you look at is look at all your answer choices. They're all units of kilojoule. All right, so you're given a measurement with moles. You're given a measurement with kilojoules per mole, but you want the answer to just be kilojoules, right? So what are you going to do here? Okay, so we noticed all the kilojoules. So even if we have no idea what the molar heat of fusion is or what moles are, we can answer this question using dimensional analysis. Okay, so you have 25 moles. You know that if you have a measurement unit per unit, so energy per mole in this case, you can make it into a conversion factor. Okay, you can make it an inequality, and from an equality, you can make your 2 conversion factors. So the goal is take your 25 moles and convert it to kilojoules using this as a conversion factor. Okay, so we know that measurement we should interpret this way: 6.01 kilojoules equals 1 mole. And so I could say 6.01 kilojoules divided by 1 mole, or I could flip that and say 1 mole divided by 6.01 kilojoules, right? I have 25 moles of something, water in this case, multiply it by this ratio, okay? So this part of the equality on top, that part of the equality on the bottom, okay? We'll notice that moles cancel out, right? And we're left with kilojoules, so 25 times 6.01, that'll cancel out moles. I'll get kilojoules, and so I go back up here, and I know my answer is A. Okay, fantastic. All right, so even if we don't know what that means, and we'll do calculations like this, we won't get to calculations like this until like unit 7 or 8, I want to say. So like we'll do calculations like this, but if you already understand dimensional analysis, you can do calculations like this already. Now, hopefully we understand what we just calculated there eventually. But if we understand dimensional analysis, we can answer questions like this no problem, even if we don't know. All right, so let's kind of put it together for this unit, right? So this unit, we want to do dimensional analysis. We're going to learn what molar mass is, and we're going to learn what a mole is. And so how do we do it in dimensional analysis? So it says how many molecules of carbon dioxide, that gives the formula for carbon dioxide, CO2, are found in 55 gram sample of the compound. So we have 55 grams of CO2, and we want to know how many molecules, how many particles that is, okay, of CO2. We're given the molar mass. Now, eventually, we're going to learn how to calculate the molar mass of CO2. Okay, but they give it to us and it's 44.01 grams per mole. Okay, fantastic. All right, now the other thing we should understand is 1 mole of a compound, that should have one more zero there. It's just the formatting thing that Word's not letting me do. 1 mole of a compound is equal to this many particles, so molecules of the compound. Okay, so we have an equality of moles and particles, moles and molecules, and what we want to understand is molar mass gives us an equality of grams and moles. Okay, so I was given this about CO2. This is the molar mass of CO2. So this is how I can interpret it. 4.01 grams of CO2 is equal to 1 mole of CO2. Okay, you don't have to put of CO2 each time, so I'm just simplifying it, but that's what it means. 44.01 grams of CO2 equals 1 mole of CO2. All right, so what do? We take our 55 grams, that's the measurement we started with, 55 grams of CO2. And what I would do is I would use my ratio, divide by the molar mass, right? Because I want to cancel out grams, right? So I'm using this equality, I'm putting the grams part on the bottom and the moles part on the top. So 55 divided by 44.01 would cancel out grams and give me moles of CO2. And then using this equality here, I put molecules on top, so Avogadro's number of molecules on top, 1 mole on the bottom. So grams are going to cancel out, and then moles are going to cancel out. Mathematically, all I have to do is take 55 divided by 44.01 and then multiply it by Avogadro's number, and then that would tell me how many molecules are in the sample. So again, in dimensional analysis, we're not changing the value of the measurement, we're just changing the unit. This many molecules of CO2 would have a mass of 55 grams. So this equals that. All right, so all we're doing is changing the units, changing the dimensions. Dimensional analysis, that's all it is. All right, so hopefully you find this helpful. You know, and if you read your handouts, you pay attention in class, you should be able to do your 1-4 assessments, no problem. It just takes practice. And so hopefully this video helps you.